Okay, my people, we are back. We're going to be focusing now on just one of the three tests. This one's called the Chi-Squared test for the goodness of fit. This is only dealing with section 1 in here, so from chapter 11. So I'm going to be using this PowerPoint. Their PowerPoint for this particular section is outstanding, so let's get started. So there's really 4 skills and 4 objectives they want you to do. Let's keep these in mind as we go through this. They want to be able to state the appropriate hypotheses. That's quite different than our significance test. So we want to be able to look out for that. That's going to be mostly a verbal description. Okay, we need to calculate the chi-squared statistic, which we have yet to do. We haven't seen any examples of how to do that. We also need to calculate the degrees of freedom, which we've never done before. And then we're going to get our p-value from that chi-squared statistic. We're going to learn how to do a 4-step process. That's what's going on in here. And then after we do a 4-step process, there's always some sort of follow-up if we reject a null hypothesis. We kind of want to know, well, where did we go wrong? Is it one aspect of this categorical variable? Is there 2? Is there 3 different things that can that are leading to us rejecting the null? So we're going to go over that details at the very end. Okay, so this is just outlining all 3 tests in here, and we're going to focus on the first one, which is the test for the goodness of fit. So we have this first example in here, which we're going to use from a bag of M&Ms. This bag of M&Ms has 60 total M&Ms in it, and the company is declaring what each and every single bag, the proportion of colors that you would expect to see in any given bag of M&Ms. So they're saying, look, 13% of the colors will be brown and reds, 14% are yellows, 16% are greens, and so forth. And the last one here is 24% should be the blue. Blue is their most popular color, and that's what we'd expect in any given bag of M&Ms, whether it's 60 or 1,000 M&Ms in a big bag or a really tiny bag. We would expect 24% of the colors to be blue, for example. So in this sample, what happened? They took a sample. They took one bag of M&Ms that was size 60, and then they found these observed counts. So here we are. We got 9 blue ones. Huh. Notice 9 is not a probability here. 9 is a count. We observed 9 blue ones out of our particular bag. So here, the sample proportion is 9 out of 60, which is 0.15. And some of you are like, oh, that's the number I want to use. No, we don't end up using this number. Well, Ms. Keys, they showed us it's 24%. We should be comparing that to 0.15 in here. It turns out we don't care about the proportions. We care about the counts. So that's going to be the biggest hurdle to get over. When we start doing our calculations, don't worry about the proportions. Yeah, we may use those to find the expected counts, but the formula for the chi-squared statistic is only going to be dealing with the observed counts versus the expected counts, which you don't quite see up here. Keep in mind, these percentages will be used to find the expected counts. These are expected proportions, not expected counts. So really try to keep that clear in your mind. So here we go. Here's all our observed counts in here. And we have, this is 15%. So if you go back a chapter and go, all right, Ms. Keys, I know how to do this. We are going to find the null hypothesis is, hey, the blue team should be 24. The alternative is it's not 24, okay? Well, this is a one sample z-test to test whether or not blue is on target or not. And so this is not going to work for, notice, orange or green or yellow or red or brown. This is only a test, a one sample z-test for blue. So think of the goodness of fit test as really a brand new test that's going to be able to take into account all colors, not just the blue team in here. So that may feel very blurry at first, but keep that in mind. So we have been down this road before, but that would have been just assessing some very particular characteristic of this bag, and that's meaning just the blue proportion, not taking into account any of the other ones in here. So that's why we come up with the goodness of fit test. It's really going to be a summary of how good all of the colors are um, are close to the stated color distribution. And that's what's going on in here. So this is our null hypothesis for the chi-squared goodness of fit test. Notice we're not focusing on blue here. We're not focusing on red or orange or yellow or brown or anything. We are stating in words what the null hypothesis is. Well, it's the company's stated color distribution for M&M milk chocolate candies, and we're stating that that is correct. That's our null hypothesis. That's what the company is stating, so that's what we're going to believe at first. That is our null hypothesis. Well, that leads us to, well, what's the alternative hypothesis? Again, this is described in words. Well, if the null is they are correct, the alternative is going to be the exactly the same description, except it's going to be not correct. So one is correct, the other one is not correct. How much more not correct? Don't worry about that right now. Just understand the claim is M&Ms, they are not lying to us. Whatever they tell us it's supposed to be, that's what it is. Versus we come along and go, you know what? These colors, they're just not matching up. Notice I didn't say which color. I just said all the colors. The color distribution is not correct. All of them. So what this is a longer way to explain what we just did. They want you to explain it in some sort of verbal manner like we just saw right here. And what are they giving you? They're giving you the option to state the null and the alternative hypothesis with this particular notation. So if you feel comfortable in this notation, then fine, but it's a lot easier just describing it in words. So we have been down this road before. This book, AP Statistics, has a dozen different p-values. P hat, p naught, P just P sub 1, P sub 2, P sub C, P value, capital P's, lowercase p's. Well, if you liked your P's, look, you got 6 more here, you got a 7th one over here. So it could be very, very blurry with all these P values. So this is an alternative. This is the mainstream, how we usually state our hypotheses in a written format of what's going on. So take a look at this right here. This is an alternative way where you state each of the 6 probabilities of what it's supposed to be. And then the alternative is kind of worded in a little weird way here. It says, well, at least 2 of them are incorrect. Well, if one of them is incorrect, that implies that at least 2 are going to be, and that's what it's staying in here. So you can't have one of them to be off, because if you think about this zero-sum game in here, if one of them happens to be higher than 24, then one of the other ones is going to be, or at least one of the other ones is going to be lower than their stated value in here. Because again, it all has to add up to be 100% or 1 in this case. All right, so let's move on. Keep in mind, our calculations are going to be dealing with observed counts and expected counts. These are not observed counts or expected counts. This is the expected probabilities of the stated distribution. Okay, so let's figure out how to find the chi-squared statistic, which is basically just chi-squared. So they're coming along and saying 24% of all bags should be blue. Well, how do we convert that into an expected count? Well, it's real easy. Well, since this one bag is 60 candies, we times it by 0.24 and we get 14.4. Excuse, do we round this number? No, you do not. Expected counts. Yes, we know there cannot be 14.4 exactly in a bag, but that's the number we use for the official expected count when the bag is sub size 16 here. So we could do this for all the other expected counts. Here are the 5 remaining colors. So we take our 60, which is the size of our bag, and times it by the stated color distribution of what M&M's says they're supposed to be, and we get these other 5 numbers, which leads us to our comparison between all 6 colors in here, and we have one column of our expected counts. That's these guys right there, including the blue team, which was done at first at 14.4. And this is what the company, this is what we found in our one bag. Notice that was our observed one bag. So our one sample here had 9 out of 60. If you add up all 60 of these numbers, you're going to get 60. If you add up all 6 of these numbers, you're going to get 60 as well. So keep in mind, these are expected counts and these are observed counts. What would the company like to see? The company would like to see these two values very, very close to one another. And that would give evidence that they are telling the truth. Notice when these numbers are far apart, that is evidence that the company is lying. You want to keep that in mind as we move forward. Okay, so let's find the chi-squared statistic. Well, this would be a graph of the comparison of that particular chart from right here. Notice we have some that are larger the expected, and we have some that are smaller from the expected versus observed. And that's what we're seeing right here in this little side-by-side bar graph in here from all the different colors. We have observed the blue team, and we have red as the expected team. And as you can see, sometimes the red team tired, sometimes the red team is lower, and so forth. And that's pretty normal. But what we're trying to get after here is, we have some of them that have large discrepancies between the two. Some of them, like this one, well, it's kind of close. And so if these are far apart, that's going to be giving us a chi-squared statistic that is quite large. And so if we see some fairly large differences between observed and expected counts in several color categories, how likely is it that those differences, this large or larger, would occur by chance in random samples of size 60 from that population distribution? So that's where our p-value is going to come into play, that probability of that particular difference occurring. So to answer this question, we have to calculate a statistic, and we call that the chi-squared statistic. Here is the formula for the chi-squared statistic. I mentioned earlier, it is the sum of all of the differences between the observed counts, the expected counts, and then you square that number and then divide it by expected. And then you're going to be adding all those numbers up. And that turns into our chi-squared statistic. So let's do that for our first example in here. So what's going on? We take our observed minus expected, square it, and then divide it by its expected value. Then we do the same for the orange team. We do 8 minus 12 squared divided by 12. Notice the expected is different for all of these values in here. Well, these two are the same, but that's just a coincidence, right? Because the stated color distribution said that the red and browns had the same probability. So the grand total of all those differences actually equals 10.18. This is not a probability. This is what we call the chi-squared statistic. This is our line in the sand that's going to determine what is our p-value. So what do we do from there? Well, let's go back and read that. Think of chi-squared as a measure of a distance of the observed counts from the expected counts. Larger values are stronger evidence against the null, and the observed counts, because they say that the observed counts are far from what we would expect. Small values Small values of chi-square suggest that the data is consistent with the null hypothesis. Okay, let's stop this video. I'm going to charge things up and we're going to get started here in a moment.